Okay, hello and welcome to another neural net and TensorFlow tutorial. Today we're just going to do a neural net in only NumPy. And I'm going to show you step by step of how we do backpropagation. So uh, I actually have like pre-written code right now. I tried to do it like live and record as I was writing, but I kept making too many mistakes. So I wrote it and I'm just going to run through what's going on. Okay, first of all, so here's like a data set I stole. What we're going to do is try and classify all these classes. And we can't do that with um, any linear thing because as you can see it's kind of like a spiral. So we would have to use a neural net to classify this. And that's all this thing is. It just kind of creates data. We have our hyperparameters. We're going to do 3-layer. We got hidden layer with 100, hidden layer 200. We initialize our weights and biases to make sure it works together. We have our number of inputs and our number of classes. I pre-wrote all our nonlinearities, our activation functions. So we got ReLU, sigmoid, tanh, and as well as their derivatives. Here's a softmax, and what this is going to do is kind of reduce a row of data into, so they kind of sum up to one. So think of it kind of like a percentage. You get uh, one number and you divide it by the total number, and then you get and you add those up, you get 100. It's basically that with the exponent. And what this is going to do is give us a nicer squash of our data instead of like a kind of uniform uh, distribution you get from a percentage. But that's all that is. We have here's our training loop. Um, you might recognize this. We do matrix multiplication, our input data, weight 1, add our bias, throw nonlinearity or activation function, ReLU. We get our output, then we get our prediction, which we're going to throw into a softmax. Here is our loss function. We're going to do cross entropy with logits. Don't worry if this doesn't make much sense right now, but it's kind of a loss function, kind of like mean square, but it's better for predictions. Okay, so let's get into backpropagation. We gotta get first. We gotta get our derivatives of our scores. So what we're gonna do, I gave a little example here. Uh, so say this is our output. It runs up to 1. Now, how do we get the derivative? Well, there's kind of a nice simple derivative, but what you do is you go through all of them. At the index of the correct answer, you just subtract 1 to it. So say our first index is the right answer, we just subtract 1, and that's our kind of derivative at their score. Pretty convenient that the math works out that cleanly. I'm not really sure why it does, but I do know that it does. Okay, so that's our derivative delta scores, and we're going to divide by our number of examples. Okay, don't need this right now. So we're going to try and find our derivative at our weight 3. So we have a function f x w equals x times w. Now, what we want to do is find the partial derivative of f with respect to w. So how are we going to do that? We're going to treat w as our variable and x as our constant. And when we find the derivative, our w is going to become a 1, and we're going to left with x. So this is what we're doing here. So x in this case is the output of layer 2. Now we're going to apply the chain rule and multiply it by the gradient that came forward, which in this case is our delta score. So now we have the partial derivative with w, and then when we get to the end, we'll move it forward. Okay, so let's get another one. Let's do the bias, and let's call this G, and it's going to be B times F of XW, I guess. I don't know. And this is going to equal F of x and w plus b. So here's our kind of multiply gate, and then we're going to addition gate. So what we're going to do is treat, when we need the delta b, I guess you could say, we're going to treat b as our variable, and everything else is our constant. So b is going to become 1 once we take the derivative, and this is going to disappear. Okay, and then we're going to apply the chain rule and multiply it by the gradient that came before it. So, well, we're just going to do 1 time, so we don't actually have to do anything. And we're going to sum it up and just kind of reduce it down so we can use it with our biases. Keep dimensions, it just kind of keeps the dimensions, I guess, I don't know. Okay, now we're on hidden layer 2. And this is kind of our x, so we treat x as a variable, w as our constant, same way up here, and we're going to get weight 3 and multiply it by our previous derivative at that point, which is still our delta scores. Just a quick note on these t's, that's just transpose. So it'll turn a 2 by 3 matrix, and that's going to equal 3 by 2. We flip it because remember the shape of our matrix matters when we're multiplying it. So if we want to multiply it back, we got to flip it kind of. So remember it was like n by a multiplied by an a by m is going to give us an n by m matrix. Now if we want to multiply these two together, we're going to have to flip this one, and that's just the transpose. So don't worry about that, it's pretty simple, I guess. Uh-oh. Okay, so we have all 3 of our variables. Now when we go back, we've done all 3. Now we just got to do the ReLU part. And so the ReLU, remember, it's just max 0x. So the derivative would either be 1 or 0. So if it's x, we take a derivative, it's going to be equal 1. If not, it's going to be equal 0. So when we're going back, what we're doing here is every number less than 0, we're just going to set to 0. It's basically multiplying by 0. And everything else, we're going to multiply by 1, which doesn't change anything, so we can just leave it as is. Okay, then we just keep applying this same back propagation, except instead of the gradient before being d-scores, it's going to be our hidden, the output of this layer. And we do the same thing. I just copied and pasted this, and just changed the number, so it's the exact same thing. We go to the first one. The only difference is we don't have to find the derivative of the input because we're not using it anymore. So that's how we did the back propagation. Last step, we got to update our parameters. So weight 1, we take the negative derivative at delta weight 1, multiply by our learning rate. We do the same for every single parameter. And that is back propagation, and that is our number. So let's just run this. And sure enough, our loss is decreasing. So our predictions are going to get better over time. And yeah, it looked pretty good. Okay, so that's it for now. Thanks for watching.